This is the first half of our Chapter 27 notes on quantum theory. We'll look at electromagnetic waves in more detail and discuss some phenomena where light behaves like a particle. First, though, we'll go back and review electromagnetic waves. Remember that we have different names for different segments of the EM spectrum, but all of these waves are essentially the same. They just have different frequencies and wavelengths. And now that we've discussed electricity and magnetism, we can describe electromagnetic radiation in a little more detail. James Maxwell is famous for developing a set of 4 equations which unified scientists' understanding of electricity, magnetism, and light. From these equations, he was able to show that light travels as an EM wave with a constant velocity in a vacuum. You can use an antenna connected to an AC generator to produce electromagnetic waves. If we look at a point near the antenna, we can imagine what happens to the electric field as the current oscillates. We can see that there is initially no field at t equals 0 seconds. Sometime later there is a downward electric field. It then returns to 0 before switching to an upward field. And after enough time has passed, you can see that we have a full sine wave representing the electric field that's been produced. Along with the electric field, there's also a magnetic field being produced by this current. Remember from our right-hand rule that the magnetic field loops around the current. So when the current moves upward through the antenna, the magnetic field would loop around counterclockwise if you were viewing this from above. At point P, the same point we were looking at the last slide, you can see there is also a magnetic field being produced at that point with a direction that's perpendicular to the electric field. So the current, electric field, and magnetic field all would look like a sine curve if we graphed their magnitudes versus time. These changing electric and magnetic fields propagate through space as an electromagnetic wave. So this could be a radio wave, light wave, X-ray, etc., depending on the frequency. EM waves are transverse waves, as these oscillations are perpendicular to the direction of travel. Here in the diagram, the electric field oscillates in the Y direction, the magnetic field oscillates in the Z direction, and the wave moves in the X direction, which is perpendicular to both of the fields. EM waves are also field waves. They're not mechanical waves, meaning we don't have any physical object or particles that are oscillating. So I mentioned earlier that Maxwell connected these different E and M equations, often modifying them in some way. His equations are all differential equations, and the only one that we see in this class is our simplified version of Faraday's law. One significant consequence of Maxwell's equations was the determination of the speed of electromagnetic waves in a vacuum. That speed is equal to 1 over the square root of epsilon naught times mu naught. So you end up with that speed of 3 times 10 to the 8 meters per second. Remember, we've seen epsilon naught and mu naught before in some of our equations. Epsilon naught is known as vacuum permittivity. And you can think of it as how easily electric fields extend through a vacuum. By the way, that is definitely an oversimplification, but it's good enough for us. And mu naught is essentially the same thing, but for magnetic fields. And that speed of 3 times 10 to the 8 meters per second has been confirmed experimentally. We've seen this electromagnetic spectrum before. For all of these waves, remember we can use our wave equation with c as the velocity of the wave if it's traveling through a vacuum or through air. You should also be familiar with where the different types of waves and visible light fall on the spectrum and how their wavelengths and frequencies compare to each other. For visible light waves, it's nice to remember that the wavelength will fall between 400 nanometers for violet light and 750 nanometers for red light. Quantum mechanics is the study of very small particles, such as photons and electrons. If you took Spanish, you probably won't be too surprised that the Latin word quantum translates to how much, and quantum mechanics is necessary to explain phenomena we will be looking at. So that includes cathode rays, which you likely learned about in chemistry, black body radiation, which does not mean the object is black in color, by the way, the photoelectric effect, and Compton scattering. So cathode rays are produced by gas discharge tubes, which are glass tubes containing a gas at low pressure. There are two metal electrodes embedded in the tube, and you can connect these to a strong battery or voltage source. When connected, you have a beam that passes through the glass tube. J.J. Thomson experimented with these cathode rays, testing the effects of electric fields and magnetic fields. From his measurements, he was able to calculate the charge per mass ratio, which was equal to the value shown. He also discovered that the cathode rays did not depend on the gas or the metal used, so he deduced that the rays contained some fundamental particle of atoms. Robert Millikan later was able to find the charge of a single electron by setting the electric force equal to the force of gravity. He did this by spraying droplets of oil into a uniform electric field and watching for zero acceleration. From that, he correctly calculated the charge of a single electron. He then plugged this value back into J.J. Thomson's charge per mass ratio, which allowed him to determine the mass of the electron and show that they were smaller than a single atom. Moving on to blackbody radiation, which describes how objects emit these electromagnetic waves depending on their temperature. We will mostly be studying what this graph tells us. This green line represents an object that's at 6,000 Kelvin, and the orange and red lines represent cooler temperatures. With the green line, we see the greatest intensity of radiation, and we also see that the peak intensity occurs at the smallest wavelength, which corresponds to the highest frequency. In other words, hotter objects emit more light, and they emit light at higher frequencies. Cooler objects will emit less electromagnetic radiation, and they will do so at lower frequencies. So as a red-hot piece of iron cools, it may stop emitting red light, but it would still emit infrared light. The main equation with photons that you should be familiar with is the equation relating the energy of a photon to a constant h times the frequency. This constant, known as Planck's constant, also pronounced Planck's constant, is a tiny number. It's 6.626 times 10 to the negative 34th joules times seconds. Einstein was able to apply this equation to the results seen in the photoelectric effect experiment, where light hits a metal and that metal can then eject or emit electrons. The photoelectric effect showed that the energy of the emitted electrons depended on the frequency of light, not the amplitude. So this is one huge piece of evidence that light can behave as a particle, not as a wave. So recall that the electric potential energy is equal to charge times voltage, or charge times electric potential. 1 joule of energy is also equivalent to 1.6 times 10 to the negative 19th electron volts. This new unit for energy is more convenient when we're talking about the energy of individual photons or electrons. Also remember that higher frequencies have higher energies, which is one reason why X-rays and gamma rays can be so dangerous. In this diagram, by the way, the left side has higher frequencies and energies. With the photoelectric effect, if light is behaving like a wave, the number of electrons emitted and their energy should increase with the intensity of light. The frequency should not have any effect on the energy. But what was found in the experiment was that the intensity did not affect the maximum energy of the electrons. Scientists also found that there was a minimum frequency of light needed to emit electrons, and that the kinetic energy of the electrons increased linearly with frequency. So this graph on the left shows the maximum kinetic energy of the emitted electrons versus the frequency of light that's hitting the metal. Notice here the F naught. This is the minimum or threshold frequency that's needed to emit electrons. Once you reach that minimum frequency, higher frequencies result in a proportionally higher kinetic energy, and the slope on that line would be equal to h, Planck's constant. That's from the equation E equals hf. That minimum frequency corresponds to a minimum energy needed to emit electrons, which is known as the work function. This is either written as phi or W naught, and this leads us to the photoelectric effect equation that is on our equation sheet. So we have K max, that's the max kinetic energy of emitted electrons, equals HF, the energy of the light that's hitting the metal, minus our work function, phi. You can think of the work function as the energy needed to separate the electron from the atom. This would also be our y-intercept if it was shown on the previous graph. The figure on the left shows the photoelectric effect. So light hits the metal cathode, causing electrons to be emitted. They travel over to the anode, and then we use an ammeter to measure those emitted electrons. If we reversed the battery, there's a certain voltage that would be needed to prevent the emission of electrons for that same frequency of light. This is known as the stopping voltage, and it's written as Vs. Again, if we think about this in terms of energy, we could have Q times Vs and set that equal to our K max. You can think of this stopping voltage or stopping potential in terms of energy. So it's an additional amount of energy needed to emit electrons. We can simplify that equation a little, replacing Q with the charge of the electron, E. We've also factored out H from both terms in the original photoelectric effect equation, so the work function term reduces to F naught. Remember that work function is an energy, and H times F is equal to energy.